Welcome back, everyone. Today we're going to begin Chapter 4. We're going to be talking about spectroscopy. Now take a look at this picture right here. This is the visible spectrum, so from red to blue, of the star Procyon. If you take a close look, you see a bunch of little dark lines that are interrupting these beautiful colors. Now those dark lines are caused by the absorption of light in the hot star's cooler atmosphere. Now the whole spectrum is normally 6 meters or about 20 feet across. But in order to display it on a single page, the full spectrum is cut into dozens of horizontal segments and then stacked vertically. So in this chapter, we're going to talk about what the spectral lines are. We're going to introduce the atoms and radiation, how the formation of spectral lines takes place, what molecules are, and how we can analyze the spectral lines that we see. So let's take a look at this diagram right here. This is a simplification of what is called a spectroscope. It's an arrangement that splits light into its component colors, meaning its different wavelengths and frequencies. If you take a look at this illustration beginning from the left, we have a light source, a hot bulb. It's emitting light or radiation in all directions. If we put a lens in front of this light source, then the light rays are going to change trajectory. They're going to come out of the lens parallel to each other. If we have them go through a slit, so we have a barrier and we cut a hole through it, then what's going to go through the slit is going to be the narrow beam of light. Then we introduce a prism in the way that has the ability to spread out the colors into the rainbow colors, so from red to blue. And then if we use another lens, that can focus those colors on a screen, and we end up seeing the rainbow on the screen or the detector on the far right. Now, I know this illustration is a little bit complex, so don't worry about it. The only important point is that light from any object, whether it's a light bulb or a star, can be spread out into a rainbow of colors, which is what we call the spectrum. Now, a spectrum is a picture of how much light is at each wavelength. And this diagram right here shows what we call a continuous spectrum. So what is a continuous spectrum? I want you to think about it as the continuous range of frequencies or wavelengths emitted by any object. It is something like the black bodies we discussed in Chapter 3. Now, if you take a look at the top, frame A, we see the familiar rainbow of colors that are spread out once light goes through a prism. On part B, on frame B, on the other hand, we see light from an excited hydrogen gas, a heated hydrogen gas, that goes through the similar arrangement of a slit and a prism. But what we end up seeing on the screen instead is a series of distinct bright spectral lines, which are called emission lines. So emission lines are single frequencies or wavelengths that are emitted by particular atoms in a hot gas. Notice how I underlined hot gas, so that is important. We get emission lines, meaning those bright lines against a black background, when we have a hot gas, meaning a heated gas. On the other hand, we can have what we call an absorption spectrum, which is a similar situation, but now we have a cool gas instead. So if you look at the arrangement in the frame right here, when cool gas is placed between a source of continuous radiation, such as a hot light bulb, and a detector or screen, the resulting color spectrum is crossed by a series of dark absorption lines. These lines are formed when the intervening cool gas absorbs certain wavelengths or colors from the original beam of light. The absorption lines appear at precisely the same wavelengths as the emission lines that would be produced if the gas were heated to high temperatures. So absorption spectrum takes place when you have a continuous spectrum that passes through a cool gas, and the atoms of the gas absorb some of the frequencies they emit. So you end up seeing those black lines, which we call absorption lines, on the screen. Now if you take a look at frame B, that's an everyday analogy for any of these line spectra we talked about, and this is an example of a supermarket barcode that uniquely determines the cost of a product. So it is a similar idea. Spectral lines. So I want you to think of spectral lines, whether they're emission or absorption lines, as the very narrow, well-defined wavelength regions in the spectrum where excess photon energy appears, if it is emission lines, or where photons are missing, if it is absorption lines. Now, I put a picture right here, and this is not in your book, but I wanted you to see the representation of a spectrum, both in terms of the continuous band of lights, but also as an intensity versus wavelength graph. So let's take a look at the graph carefully. Notice on the y-axis we have intensity, on the x-axis we have wavelength, going from ultraviolet to infrared, which corresponds on the colors you see underneath in the spectrum. Now, notice how when we have a continuous spectrum, so no black lines along the way, it is a continuous line, just like it shows on the graph. If we have the absorption part, so we see black lines along our continuous color of bands, it shows on the graph as those little dips. Those are the absorption lines. On the other hand, if we have emission lines, which are represented on the left side of the graph, we have spikes in intensity instead. Now, spectra of astrophysical objects are usually a combination of these three basic types: a continuous spectrum on a part of the spectrum, absorption lines or different parts, and emission lines on yet other parts. So it is a combination. Now, in accordance with the convention adopted throughout the text, in most of the pictures you're going to see frequency increases towards the right. And note that wavelengths shorter than approximately 400 nanometers here are going to be shown in the color purple or shades of purple. They're really in the ultraviolet part of the spectrum, which is not visible to the human eye. And anything beyond the red on the other end, which would be infrared, would also not be visible to the human eye. The emission spectrum in general can be used to identify the elements within an astronomical object. Each element has a distinct emission spectrum. The first spectrum you see on the top is the emission spectrum of hydrogen. So if we look at a celestial object and we see those lines, you see how there's a red line that corresponds to about 660 nanometers. And then we see some purple lines towards the 380 nanometers. Then if we find this exact combination, we know that this is hydrogen. And the same thing for sodium, helium, and so on and so forth. Each element has its own unique identification spectrum. Right here, this is the emission and absorption spectrum of the element sodium. So on the very top one, we see the emission, and on the very bottom one, frame B, we see the absorption. So the two bright lines in the center on frame A appear in the yellow part of the spectrum. And on frame B, the two dark lines appear at exactly the same wavelengths as the bright lines in the sodium emission spectrum. Now let's take a look at this one more time, because I want to make sure everybody understands this, because this is very important. So here's a continuous spectrum. We can get a continuous spectrum if we have a hot source of light. Once we get that light going through a slit and a prism, we end up seeing a continuous band of colors from shades of purple to shades of red. If we were to represent that in a graph of intensity versus wavelength, it would look like a continuous line. So the spectrum of a common light bulb, for example, or another way of saying light bulb is incandescent light bulb, would span all the visible wavelengths without any interruption, without any spikes. An emission line spectrum, on the other hand, is produced when we have a hot cloud of gas which will emit only at specific wavelengths, and that depends on the gas's composition, so what it's made of, and its temperature. The end result, once it goes through the spectrometer, is the production of a spectrum with bright emission lines. So what you will see is a dark background with some bright emission lines. In an intensity wavelength graph, you will see spikes, which correspond to the emission lines. An absorption line spectrum, on the other hand, takes place when you have a hot light source, but between your light source and your spectrometer, there's a cloud of cool gas. Now, that's going to absorb light of specific wavelengths, which has the end result of seeing a spectrum with absorption lines. Whenever you see that, you will see the background of the visible light colors, and then it's going to be interrupted with certain lines of black lines, which we called absorption lines. On the graph, on the other hand, on intensity versus wavelength, you will see that continuous line we talked about before on the continuous spectrum, but you will also see those dips in intensity, which will correspond to the absorption line wavelength produced by this cool gas that's between us and the original light source. Here's another representation right here. So on the top frame on the left, we have a source that's about 6,000 Kelvin. 6,000 Kelvin is the surface temperature of our sun. Now, if between the sun and us there's a cloud that has a temperature that's less than the sun, so that's cooler, let's say 5,000 Kelvin, then what we will end up seeing, because we have that cool gas on the way, we end up seeing the absorption lines, because that cool gas is absorbing some of that wavelength. So the thin gas on the top is cooler, so the end result is absorption lines. If you take a look at the bottom part of the picture, if we have empty space on one side on the left, and between the empty space and us, we have a hot gas, something that's hotter, let's say 5,000 Kelvin, then the end result is emission lines. So we end up seeing an emission spectrum. Now here is the sun's spectrum. Why are there no lines in the continuous spectrum? Well, spectral lines are chemical fingerprints telling us which elements and how much of each is contained in the object we're observing. So in a continuous spectrum, we will see all the wavelengths. In the spectrum of the sun, which is the second one, some of them are going to be missing. And then if you take a look at the spectrum from then on and down, you see they're mostly black. And then there's some lines of bright lines that you see. That's emission spectrum. So those are emission lines of the elements represented over there, starting with sodium, and there's calcium there, etc. The three spectra are represented by what we call Kirchhoff's laws. Now, put laws in quotation marks because they're not really laws, they're mostly rules. They're not like Newton's laws, for example. Now, Kirchhoff's laws tell us that luminous, meaning a source that provides light, so a luminous solid liquid or dense gas will produce a continuous spectrum. A low density hot gas will produce an emission spectrum. And a continuous spectrum incident on a cool thin gas will produce an absorption spectrum. Here is a representation of Kirchhoff's laws. So we have a source of continuous radiation, which is represented right here by the light bulb right in the center of this picture. If you look at frame A on the bottom, if we have an unimpeded beam of light from the light bulb, we end up seeing, after we put it through the prism, we end up seeing a continuous spectrum of lights, a continuous spectrum of colors. If you take a look at frame B on the left, when the source is viewed through a cloud of hydrogen gas, a series of dark hydrogen absorption lines will appear in the continuous spectrum. If the gas cloud is made out of helium, then we would end up seeing the dark helium absorption lines. Now these lines are formed when the gas absorbs some of the bulb's radiation and re-emits it in random directions. Because most of the re-emitted radiation does not go through the slit, the effect is to remove the absorbed radiation from the light that reaches the screen at the left. Taking a look at frame C, when the gas is viewed from the side, so the cloud itself, a fainter hydrogen emission spectrum is seen consisting of re-emitted radiation. The absorption lines in B and the emission lines in C have the same wavelengths because they're produced by the same gas cloud, hydrogen in this case. Now in terms of astronomy, well, the gas cloud could be the atmosphere of a star or planet. So when we're looking at things up in the sky, there's so many other things that could be on the way. Maybe a gas cloud, maybe a nebula, maybe different layers of the star's atmosphere. So that results in a more complicated emission and absorption spectrum. Now I would like to talk about atoms and radiation. Once we discovered the existence of spectral lines, physicists realized that they needed a new model to explain how the atom behaves. And Bohr came up with a model that had certain allowed orbits for the electron. Now this representation right here is a hydrogen atom. The hydrogen atom is the simplest element in the periodic table. It is comprised of one proton in its nucleus, orbited by one electron. And this is it. This is a hydrogen atom. On frame A, you see the ground state of this atom. And on frame B, the same hydrogen atom, but in its excited state. So this is the early 20th century conception of the hydrogen atom, which is what we call the Bohr model. And what you see in the picture is the electron orbiting the central proton in a well-defined orbit, almost like a planet orbiting the sun. Now you're seeing that in two different states. These two electron orbitals represent different energies. What is the structure of matter? Well, if we are to zoom in atoms, which make up everything, we will end up seeing not quite a circular orbit of an electron, but what we call an electron cloud. So the electron is whizzing about more of like in a spherical shell pattern rather than a circular pattern. And if we zoom in within the electron cloud, which is smaller than 10 to the minus 10 meters, then we get to see the nucleus. This picture right here happens to have both protons and neutrons. Now, just to give you an idea of sizes, if you magnify a hydrogen atom, and hydrogen atom, remember, is the one that has one proton and one electron. So if you magnify a hydrogen atom by 10 to the 12, that's 1 followed by 12 zeros, then we're making the nucleus, meaning the proton, the size of a grape seed. And the diameter of the electron cloud about 4.5 times larger than a football field. So that's pretty amazing. That tells you that most of the atom space is empty. We have the nucleus in the very center, lots of empty space relative to the size of the atom, and then on the outskirts is where we first see the electron. I'd like to talk a little bit about atomic terminology. What we call atomic number is the number of protons in the nucleus, and that is what defines the element. Hydrogen is defined by the fact that it has atomic number of 1. Helium, the second element in the periodic table, has atomic number 2. And so on and so forth. On the other hand, atomic mass number is the number of protons and neutrons. Both protons and neutrons are found in the nucleus. So we have the nucleus in the center that is comprised of protons and neutrons, and then we have electrons that are orbiting that nucleus in that shell cloud pattern. So if you take a look at hydrogen, whose symbol is capital H, hydrogen 1 tells you that it has an atomic number of 1. That 1 on the upper left corner represents the atomic mass number. So it tells you that it has 1 proton and no neutrons. Helium in the middle is written as capital H and little e, its atomic number is 2. It means it has 2 protons, and its atomic mass number is 4. So if it has 2 protons and has a total of 4 protons and neutrons, then it must have 2 neutrons, which are represented in this picture as the 2 gray spheres for neutrons and the 2 red spheres for protons. Carbon 12 in this case, which is very important because that's what life on Earth is based on, has an atomic number of 6 and an atomic mass number of 12, which means it must have 6 protons and 6 neutrons, which add up to 12. Now, molecules are a combination of 2 or more atoms. For example, water, or H2O, is a combination of hydrogen and oxygen. Carbon dioxide is a combination of carbon and oxygen. And here's a simplified version of the periodic table. There are over 100 chemical elements. The number of protons in the nucleus of an atom identifies which element it is. An atom with 1 proton would be hydrogen. An atom with 2 protons, I'm looking at the top line of the periodic table, would be helium. An atom with 3 protons would be lithium. If we jump to C, capital C, which is carbon, it has 6 protons in its nucleus. An atom with 1 more proton, so 7, is nitrogen. And an atom with 1 fewer proton is boron, and so on and so forth. And you can look this up there in the back of your book. What is an isotope? Well, an atom of a given element always has the same number of protons in its nucleus. The number of neutrons, though, is less restricted. For example, if you added a neutron to a carbon nucleus, it would still be a carbon, but it would be slightly heavier. We'll call that carbon 13 because it still has the 6 protons, but now we have 7 neutrons. Atoms in general that have the same number of protons but a different number of neutrons are called isotopes. Carbon itself has 2 stable isotopes. One contains 6 protons and 6 neutrons for a total of 12 particles, which is why it is called carbon 12, and carbon 13 has 6 protons and 7 neutrons in its nucleus. Helium 4, which is in the parentheses right there, has 2 protons and 2 neutrons, but helium 3, on the other hand, has 2 protons and 1 neutron. What about electrons? The number of electrons in an atom of a given element can vary. Protons and neutrons are bound tightly into the nucleus, but the electrons are held loosely in the electron cloud. Emission energies correspond to energy differences between allowed levels of electron orbits. So think of them like steps on a ladder. When you're climbing a ladder, you can only go between step 1 and step 2. Step 2 or step 3. There are no steps between the rungs of a ladder, and it's the exact same way in terms of the allowed energy levels for an electron. So it has to jump through certain values of steps. The modern model has the electron cloud rather than the orbit we talked about before, and that is due to quantum mechanics. Right there in the picture, is the representation of the ground state for a hydrogen atom, so one proton and one electron. And on frame B, we have an excited state where the electron, see how it's further away from the proton? It has jumped to a higher step on the ladder. I would like to talk a little bit about electron shells so that you can get a better idea of how do we know where the electrons are allowed to orbit, in which place, how far away are they from the nucleus. Electrons are bound to the atom by the attraction between their negative charge and the positive charge on the nucleus. This attraction is known as the Coulomb force. To ionize an atom, meaning to remove or add an electron to an atom, you need a certain amount of energy. And if you want to completely pull the electron away from the nucleus, you need a different amount of energy. Now, this energy is called the electron's binding energy, the energy that holds the electron into the atom, that gets it to orbit the nucleus. The size of an electron's orbit is related to the energy that binds it to the atom. If an electron orbits close to the nucleus, then it is tightly bound, and a large amount of energy is needed to pull it away. Therefore, its binding energy is large. An electron orbiting further from the nucleus is held more loosely, and less energy is needed to pull it away. That means it has less binding energy. Now, nature permits atoms only certain amounts of binding energy, which we call quanta. And the laws that describe how atoms behave are called the laws of quantum mechanics, which are beyond the scope of this class. But I do want you to know, because atoms can have only certain amounts of binding energy, the model atom can have orbits only of certain sizes, which are called permitted orbits. These are like steps in a staircase. You can stand on the number 1 step or the number 2 step, but not on the number 1 1/4, because there is no step like that. The same thing applies to the electron. The electron can occupy any permitted orbit, but there are no orbits in between. Now, this arrangement of permitted orbits depends primarily on the charge of the nucleus, which in turn depends on the number of protons within the nucleus. Consequently, each element has its own pattern of permitted orbits. So if you take a look at this picture right here, you see how for the hydrogen atom on the left, those are the permitted orbits for the electron. On the helium one, on the other hand, you see how their orbits are located at different places that correspond to different radii away from the nucleus, which corresponds to different energies. Isotopes of the same elements have nearly the same pattern because they have the same number of protons. However, ionized atoms have orbital patterns that differ from their non-ionized forms. So the arrangement of permitted orbits differs for every kind of atom and ion. The one we're going to concentrate in this class is the most basic atom, which is hydrogen. So take a look at this picture right here. This corresponds the energy levels of the hydrogen atom. Remember, this is the simplest atom in the universe, which is 1 proton and 1 electron. Now, the allowed energies of the electrons in each orbit are given by that formula right there, where capital E stands for energy. E sub n corresponds to the energy level. And that's equal to 13.6 times 1 minus 1 over n squared. And the units for energy, because we're talking about very small energies, we measure that in the units called electron volts. So that EV right there you see in the equation are the units of the equation, which are electron volts. Now, when the electron is at the closest allowable step or ladder or radius or location away from the nucleus, we call that the ground state, and we label that n equals 1. So that is n equals 1, which corresponds to 0 electron volts. The further away we move on the steps of the allowable energy for the electron, so if we look at n equals 2, the corresponding energy for that is 10.2 electron volts. You get that number by plugging that in the formula there on the left. N equals 3 is 12.1 electron volts, and so on and so forth. For n approaching infinity, we get 13.6 electron volts. And n equals infinity corresponds to ionization, which means that the electron was given enough energy to leave the atom of hydrogen to escape the force that was holding it close to the nucleus, which made this atom ionize, which means an ionized atom is an atom that is either missing or has too many electrons. In this case, if the electron has escaped, the hydrogen atom is ionized, is missing its electron. Now, the spectral lines we talked about before, we talked about the emission, the bright lines that we see on a black background, and then we talked about absorption spectrum, which is the bright background speckled with the black lines. Well, those spectral lines actually correspond to electron transitions. So energy is released when an electron drops from an upper to a lower orbit, and that causes the atom to emit light, which we know light is electromagnetic radiation. Since it emits light, it releases energy. We see it as the emission spectrum. On the other hand, energy is absorbed when an electron climbs from a lower to an upper orbit, because in order to do that, it needs to receive energy. This causes the atom to absorb light, EM radiation, so the end result is the absorption spectrum. So now you know where those emission and absorption lines come from. Now notice how in this picture there's several transition stages, and let me talk about this a little bit. We have what is called the Lyman series, which is represented by the purple arrows. The Lyman series corresponds to any kind of electron transition from any permitted orbit down to n equals 1, down to the ground state. And if the electron is jumping from n equals 2 to n equals 1, that corresponds to alpha, the first transition in the Lyman series. If it's jumping from n equals 3 to n equals 1, that's the second transition, so that corresponds to beta, and so on and so forth, following the Greek alphabet for the Lyman series. The Balmer series, on the other hand, is the allowable transitions from any orbit down to n equals 2, down to the first excited state. Now, Balmer series are very important, so I want to talk about them a little bit more. And the Balmer lines are important because they're the only hydrogen lines in the visible wavelength range. That means we can see them when we look at them. So if an electron is transitioning from n equals 2 to n equals 3, or the other way around, from n equals 3 to n equals 2, it produces the Balmer alpha line, and that corresponds to hydrogen alpha, which we can see. If we have a transition from n equals 2 to n equals 4, or the other way around, that's the second transition in the Balmer series. So we call that the Balmer beta line, and that corresponds to hydrogen beta. And those are important because those fall within the visible spectrum. And we can continue on and on with hydrogen gamma, delta, and so on and so forth. But alpha and beta are the important ones. I want to talk a little bit about the photoelectric effect, but you will not be tested on this. The reason I'm mentioning it is because Einstein won the Nobel Prize in Physics in 1921 because of his discovery of the law of the photoelectric effect. So what is the photoelectric effect? The photoelectric effect tells us that when light shines on a metal, electrons can be emitted from the outer layers of the atomic structure of that metal. The frequency must be higher than the minimum that it corresponds to the characteristic of the material that the metal is made of. If you're shining light that has higher frequency, so you're increasing the frequency, then the electrons that are emitted have more energy. If you're increasing the intensity of the light that you're shining on the metal, you get more electrons with the same energy. So you don't get electrons with higher energy, but you get more electrons with the same energy. And here's a representation right here. And the only way to truly understand the photoelectric effect is if you understand that light behaves like particles. So not just like waves that we talked about in the last chapter, but also behaves like particles. So in the picture right over here, we see when we have infrared light and red light, we have no electron emission. When we switch to the blue light, then we have a lower speed electrons, and when we switch to ultraviolet light, we have higher speed electrons. And those dials right there represent the electron energy that's being emitted from the metal. So just wanted to talk about that in a very general way. You will not be tested on it. What is very important though is figuring out the corresponding energy of the photons of the light that's being released when the electrons are jumping from one orbit to the other. Whether they're jumping to a higher orbit or a lower orbit, when they do that, they either release or absorb energy in the form of light, which is what we see as the emission and absorption spectrum. And Planck was able to figure out what that energy is equal to. And that energy is equal to h, which is a constant, we call that Planck's constant, times frequency. And remember, you may see this formula written in terms of frequency or wavelength because we can interchange each other with that formula with the speed that we have talked about before. Now the value for h is very, very, very small number. It's 6.63 times 10 to the minus 34 joules times seconds. So the energy we're talking about is very, very small. And that corresponds to the energy associated with the emission or absorption. We just finished talking about chapter 4.1 and 4.2. It is very important for you to be able to identify the three types of spectra, continuous, absorption, and emission, and understand how that is related to the basic model of the atom. As usual, don't forget to log into Mastering Astronomy and keep track of your assignments and quizzes. Until next time.